All right, welcome back. This is the second part of going through this particular lesson. We started out and I gave some examples of these first page rules. If you have not seen that video, highly recommend you take a look at that one. And we got through on that. We got through example 3 and we were moving into example 4. So let's pick it up right there. One thing that we're going to be very, very good at is when we get multiple step directions, we're going to leave some space for our answers. So I'm going to come over here right now. I'm going to go A, the extrema. B, intervals of increase. C, intervals of decrease. Oh, do we have to write that out? No, you don't have to do well on the test. The greater the test, because we're going to use up some space here, needs to see some organization. Throwing in a word occasionally in math is okay. All right, so we're going to use analytic methods. The first thing we're going to do is we're going to consider any endpoints. But I can put any value positive. They can go positive as big as I want. I can put in 0. I can put in negatives. And I'm going to get functions out. So we have no endpoints. This is an exponential function. We can consider end model behavior. As x gets big, I get e to a big power. Don't forget, e is just a number. So this thing is going to increase like crazy. As I put in a big negative, I get e to a big negative, which is 1 on e to a big positive, which is 1 over a big positive, and it wants to approach 0. It's just an exponential function. We've seen them before. In fact, that really tells me just about everything I need to know, but let's let calculus do the work. What am I saying? Well, extrema, there are no extrema because we never get to 0. We can't say that 0 is a minimum. We don't ever say infinity because that's a concept, is a maximum. The function is increasing everywhere. It's decreasing never, but let's let calculus prove it to us. So no endpoints. Next thing I want to do is find the derivative. F prime x is f of e to, or excuse me, if it's e to the derivative wants to be e to the. However, I've got an inside function 2x, the derivative of 2x is 2. So we ask, when is the slope 0? This just becomes shoe tying, robotic calculus moves. When is the slope 0? Never. When is it non-differentiable? Well, I can take any number I want times 2. I can take e to any power I want, and I can multiply any number I want by 2. So never. We're going to be doing things like this. This is just part of the Robotron portion of what we do. Our graph of f prime is always positive. Therefore, in other words, any value I put into here, I get positive values. So the slope is always positive. Therefore, we have none. It's increasing. Well, how do we state it's increasing? All real numbers? No. As an interval, negative infinity to infinity. When is the function decreasing? Never. Okay. So not a whole lot going on that one, but it's nice that, we started in an area of a function that we'd be pretty comfortable with coming up with, and the calculus still supported. So that is the process we're going to go through all the time. The only difference is lots of times we're going to have to find some specific points. Okay, so again, I'm going to start off leaving myself space for answers. Our extrema, I'm going to go in A. Our interval of increase, intervals perhaps of increase are going to go in B. And C is going to be our intervals of decrease. And the first thing we should note here is that x has to be greater than or equal to -2. We have an endpoint at -2. So I'm going to want to find f of -2, and we can quickly see f of -2 gives us, oops, this should be -2 plus 2, or 4 minus 0, 4. So we have a point at -2, 4 that might be one of our extremes. It might tell us where we increase, where we decrease, but that actually is an endpoint. All right, so next we're going to find our derivative. I'm going to treat this like y equals 4 minus x plus 2 to the 1/2. Quick warning, I've seen people do that kind of work, and then somehow or another they think they've already found the derivative. We haven't done any derivative work yet. Y prime is derivative of 4 is 0. I've got a negative. I bring the 1/2 down, negative 1/2 times x plus 2 to the negative 1/2 times the inside derivative, but the inside derivative is 1. So my derivative is negative 1 on square root 2 times square root of x plus 2. There's y prime. What do I do with y prime? I find out when the slope is 0. A fraction is 0 only when the numerator is 0. Never. When is it non-differentiable? This is non-differentiable at negative 2 or anything less than negative 2, but we're only dealing with numbers that are bigger than or equal to negative 2, and the only one of those in here is x equals negative 2 as a point of non-differentiability. Therefore, we should find that coordinate, but we've already found it. So we should have enough without even considering what the graph looks like, which we'll come back to come up to figure out, is this a max, is it a min, where are we increasing, where are we decreasing? Okay, here's my y prime, my slopes, that should be a colon, not a equal to sign. Here's our sign chart on there. I know negative 2 is an endpoint, and the slope at negative 2, let's consider this for a moment. If I put in negative 2, which I can't, I get 0 in the denominator. If I put something slightly bigger than negative 2, this becomes slightly bigger than 0 in here. The square root of that is slightly bigger than 0. 2 times that is slightly bigger than 0. Negative 1 divided by slightly bigger than 0 wants to be a huge negative. We want to approach negative infinity. This is our slope curve. Wants to look like negative infinity. So wherever my point is at negative 2, it's like coming down straight out of there. Actually, this would be negative 2, 4. We know that. It wants to be coming down as we're moving to the right, straight out of there. Now, as we proceed to put bigger and bigger numbers in, we still get a negative on positive, so my slope stays negative forever. Graph's going to look like this. Therefore, negative 2, 4 tells us that with this slope, it says we have a maximum of 4 at x equals negative 2. This function is decreasing from negative 2, not at negative 2, from negative 2 to infinity, and it increases never. Now let's go back and let's take a look at this function. We know that y equals square root of x looks like this. So what would this look like? This would be 2 to the left, up 4, upside down. 2 to the left, up 4, and upside down. There's our local maximum at 2, 4, decreases forever. Okay, a little bit more going on here. We're going to be really, really careful when we take our chain rule, or excuse me, when we take our derivative, because we have the ability to put a dot in here. Therefore, this is a product rule. Might want to treat it like x times 4 minus x to the 1/2. But before we do that, we should note that 4 minus x has to be at least 0. Therefore, x has to be less than or equal to 4. I can put 3 in here. I can barely put 4 in here. I can't put 4.01. So right away, I realize I have an endpoint at 4. So I want to consider that value. F of 4 is 4 times square root 4 minus 4, or we get the point 4, 0. I'm going to find extremas, and I suspect there's a very good chance that I have an extreme value of 0. Maybe not, but it's an endpoint. Doesn't it almost have to be, unless it's constant at that point? B, intervals of increase. And C, intervals of decrease. And we may need some room here. Okay, so very, very carefully, we're going to go through our product rule. F prime of x. First, times derivative of second 1/2 times 4 minus x to the negative 1/2 times the inside derivative times negative 1 plus the derivative of second 1 times 4 minus x to the 1/2. Okay, I cannot put this 4 minus x to the negative 1/2. I can't move that to the denominator in the whole function, but I can move it to the denominator in this because everything here is factored. This is a term. 2 goes to the denominator. In the numerator, I'm left with negative 1 times x, negative x. In the denominator, I've got a 2. I've got a square root of 4 minus x, or 4 minus x to the 1/2 if you like, plus 4 minus x to the 1/2. But I'm going to combine that into an individual fraction. The least common denominator needs a factor of 2, needs a factor of 4 minus x to the 1/2. This term does not have either of those. We need a 2 times 4 minus x to the 1/2 on a 2 times 4 minus x to the 1/2. Blocked myself in a little bit. I need to be better with that. So I get plus this at negative x. Sorry, this negative x was already over that. When I multiply this times this, I get a plus 2. Square root of this is just this, 4 minus x. Don't drop the parentheses unless you distribute. For a final derivative, f prime of x is, I get an 8 minus x minus 2 more x's minus 3x, all on 2 times 4 minus x, excuse me, to the 1/2. Okay, so first thing I want to do, I want to find out when the slope is 0. The slope is 0 when 8 minus 3x is 0, or when x equals 8/3. We got a little bit of cleaning up to do that, but I definitely want to find, I'll leave room for my decreasing interval here, I definitely want to find f of 8/3. We got a little bit of a mess here, but we're going to get through this. 8/3 square root 4 minus rats 8/3, or 8/3 square root. 4 is 12/3 minus 8/3, 4/3. Ooh, that's a little bit helpful. Square root of 4 is 2, so I have 16 on 3 root 3, or 16 root 3 on 9. And I'm going to go ahead and just get an approximation of that. And I've got that right here. Here's my 16 square root of 3 divided by 9, about 3.079. Why 3 decimals? Because that's what AP Calc Test wants us to write them as, unless otherwise specified. Okay, so I've got another ordered pair with a value of 3.079, so that makes this a very, very possible maximum point. Now, when do we have non-differentiables? Our non-differentiable occurs when x is 4. I can take the square root of 0, but I can't divide by 0. Now, it also happens when x is 5, but we've already eliminated the possibility of x being 5. So I have a non-differentiable at 4, but I've already dealt with 4. If I think about it just a tiny bit more than 0 here, let's go ahead to our f prime. Our f prime, we've got an endpoint at 4. We've got an interesting value at 3.079 where the slope is 0. At 4, if I put just a little bit less than 4 in here, a little bit less than 4, the numerator's negative, the denominator's positive, we are negative. Did I get that right? A little bit less than 4, numerator is negative, denominator a little bit less than 4 is positive. We have a slope that's negative here. In fact, we have a slope that's like negative infinity going into 4. Okay, and then if I put a value bigger than, let's see, where's my 8/3? Actually, this is 8/3 here. Sorry, this is 8/3. 8/3 gave us that slope of 0. Our slope then, yeah, I don't want the function, I want the derivative. So if I go beyond 8/3, if I put in like 0, I get positive on positive. Then the slope is positive. So here's what I've got. It's going up until it gets to this point. It levels off at 8/3. It's going down until it gets to 4. So 4 must be a local minimum. So we have a minimum of 0 at x equals 4. That's local. And we have a maximum of 3.079 at x equals 8/3. This graph increases from negative infinity to 8/3. It decreases from 8/3 until 4. So these little charts become really useful for us if we trust, hey, we've got all the places where the graph could level off. All right, took some space on that one. Hopefully I didn't borrow so much. I've left myself enough room for B. All right, let's take a look here. My first thought is, hey, maybe I've got some endpoints here, but x squared plus 4 is always greater than 0. So although this is a rational function, there are no vertical asymptotes. I've got no, this thing is a smooth curve forever. I can choose any value of x I want. However, I doubt that's the case when we find our derivative. Let's see. H prime of x is low, d high, -1, minus high, negative x, so plus x, d low, 2x, all on the square of the thing below. Well, maybe. Let's see what we get. Equals, I've got a negative x squared plus a 2x squared. Negative x squared plus 2x squared. I've got an x squared. I've got a minus 4, all on x squared plus 4 squared. Well, as it turns out, it looks like we are differentiable everywhere. I can put any value I want in the denominator here. So h prime of x gives us this. All right, I am interested when the slope is 0. That's when x squared minus 4 equals 0. That's x equals plus or minus 2. So I probably want to go back to my original function and find f of 2. F of 2 is -2 on 2 squared plus 4, or -2 on 8, or -1/4. Find f of -2. F of -2, the opposite of -2 is 2. On -2 squared plus 4 is +1/4. I'm starting to suspect perhaps this function is odd. And next we want to find points of non-diff. Our non-differentiable points, we have none. I can put anything I want in here for x at any point and never break my calculator. Okay, I'm going to do my little handy slope sign indicator. We're just doing a sign chart, S-I-G-N, not S-I-N-E. I know that we have interesting values at -2 and at 2. That's where the slope is 0. Between there, if I put in 0, I get 0 minus 4 negative on positive, I get a negative. To the right of 2, if I put in 3, I get positive on positive. To the left of -2, if I put in -2 into here, I get positive on positive. I get positive. So this curve is going up, down, up. Pretty clear what's happening here. That gives us our extrema. It gives us an extreme value. It gives us a local max. It gives us a maximum of, when we put in -2, we got out 1/4 at -2. It gives us a minimum Graph goes down and up. See how we're analyzing the slopes here? It goes down and up. Gives us a minimum of negative 1/4 at positive 2. Our graph is increasing. Any place the slope is positive, and the slope is positive from negative infinity to negative 2 in union with 2 to infinity, and C, it is decreasing when the slope is negative from negative 2 to 2. Without even looking at what the graph's doing, we can get through that, which is probably a nice way of telling a machine to figure it out for us, because the machine will have better ability just to crunch the numbers than it will to analyze a graph like a human might. So anyway, there you have it. A lot of steps to each of these problems, just not a whole lot of problems. I will have videos of each of these problems available for you in the near future. Thanks for checking it out.